Okay, hello everyone. Welcome to another episode of Q&A about history of science and technology. And I see a number of questions got saved up here. Well, let's see. David is asking, what are some of the most prominent developments in 20th century history of software design? Well, first point to make is there wasn't any software before the 20th century. The first software that existed was really in the 1950s, I would say. So, I mean, to kind of go through a little bit of the history there, the whole idea that you could make a universal computer, that is a fixed piece of hardware that you merely had to put different programs into to get it to do different things, that was something that arose kind of out of ideas in mathematics, mathematical logic, and so on, with people like Alan Turing in 1936, and then sort of that was a theoretical branch. Then there was a practical branch that came from going from electromechanical calculators to electronic computers, and that happened in the mid-1940s with things like ENIAC and so on. In the original instantiation of computers, electronic computers, there was the notion of the so-called stored program computer, the computer where you could have the data that the computer was operating on, like the numbers that it was doing calculations with and so on, was stored just as the program that specified how to do those computations, when you should add, when you should multiply, when you should branch into this conditional thing versus another. All of that was being stored in the same kind of a way that the actual data about numbers and so on was being stored, and that happened in the 1940s and so on. And the very earliest software, so to speak, was very, very low level. I mean, it really just said there's this switch that's going to be operated in this way on this computer, switch number such and such is going to be operated this way, and then this one to this way, and so on. If you look at the coding sheets that existed that specified what programs should be stored in these very early computers, they're extremely primitive. I think, well, for example, let's see, there was a computer, so there were different computers. There were computers in the US, the ENIAC, and then the EDVAC, and a series of other computers. In England, there were computers called the ACE, and so on. One computer where I happen to have looked at it a little bit is in Manchester, there was an ACE computer that Alan Turing was involved with. He wasn't, I think, very happy at the fact that people didn't listen to what he had to say about how one should do, quote, software design and so on. But anyway, I did once look at his coding sheets from that computer, and it is all kinds of crazy, weird things there, because there were things like specifying operations and so on. And there was a question of, well, in the end, they're going to be specified in terms of binary bits, but one was, he was trying to sort of write them out in an efficient way. And so he started using all the different characters on a teletype with to represent those sequences of binary bits. I mean, I think he was using basically base 32, writing out numbers in base 32, which means you've got to have, 22 things beyond the ordinary digits, and they were specified with letters and so on. And if you look at his coding sheets, they're utterly obscure. So one thing that was an early sort of discovery in software was the idea of subroutines, the idea of subfunctions. When John von Neumann was kind of writing out sort of reports about kind of what operations you might want to do on a computer, he was doing that based on sort of his understanding of mathematics and his understanding of logic. And one of the things that he famously said was, I think he said, nobody will ever want to write a program that's more than 400 lines long. Okay. So it turns out, obviously, to be completely false. There are programs that are tens of millions of lines long. Even we've created such programs, and that's what our technology stack is a probably by now 100 million line program or something. Why was John von Neumann so wrong? Well, the answer is he didn't have the idea of kind of subroutines. He thought when you wrote out a program, It was everything that was going to be done was going to be right there in the program you wrote out. It's kind of like writing out a proof in mathematics where sort of everything is there right in the proof, and you're not referring to other theorems along the way in the proof, which then have their own separate proofs. He seems to have kind of missed that idea, but that was an early kind of software idea, was the idea that you could have functions that are, or subroutines that are separately executed, that where you define that, you write the code for that, you can test that separately, you can think about it separately. It is sort of a cognitive unit that's separate from the rest of the program. Now, I think in terms of the calling of subroutines, that took a little bit of technology development to see how that would work, because when you're running a program and then you call a subroutine, you want to be able to start doing things in the subroutine and then come back from the subroutine and be back in the state ready to execute the next instruction in the main program. And that required the invention of the idea of a stack. And I'm not completely sure when stacks were first done on computers, but that was, for example, in the way that you call a subroutine and the way that you allocate memory for the local variables of the subroutine, that was not clean, at least until the C programming language came along in the 1970s. In things like Fortran, that's a much messier story. How you really allocate space on the stack. And for example, Fortran didn't have the possibility of recursively calling functions. You could, if a function couldn't call itself, that was just not allowed by the compiler in early versions of Fortran. I think because this mechanism of sort of having this stack where you could push things on the stack and keep doing that over and over again didn't really exist. So I think I would say one of the first things that was realized in kind of sort of the development of software, well, let's go through some of them. I mean, one was you can not just refer to the literal operations of the machine, the literal, move this switch from here to there. That was something where you made things, it's really been a trend of making things sort of more symbolic in some sense of symbolic. So for example, you could say, well, we're going to store these numbers in register 11. Okay, and we specifically say 11. And everywhere we reference that number, which might represent the length of some thing in some, or a time variable or something like this. No, let's say a length variable. You always say it's in register 11. Well, then people had the idea of variables, where you say it's a variable, it's called L. And we always associate L with register 11. But we can write in our programs, we can just write L, and that's an easier thing for us to remember than remembering, oh, the length is stored in register 11. So there's sort of that was another piece of progress, was the idea of having sort of variables to represent lumps of memory. Then the idea of having names to represent lumps of program, which was kind of the idea of subroutines, that you could name this lump of code and name it with the name of that subroutine, the name of that function, and just refer to it that way. So I suppose one of the early ideas was sort of this notion of give names to things, whether it's variables, where they're lumps of memory, or whether it's pieces of code. I think then, well, let's see, other kinds of important developments in terms of software. I mean, things like, well, okay, we can look at it in terms of the actual systems that were built. There was the question of what can you represent in software? What can you actually represent on a computer? The earliest idea was it's sort of a mathematics-based idea. Let's represent numbers, let's represent logical variables, true, false, and things like that. Then there was the idea of what about strings? What about character strings? And that was where in Fortran, for example, you would have these holorith. Hollerith was Herman Hollerith was a person who was an early IBMer who was responsible for tabulating machines for the Census Bureau in the early 1900s, and his name kind of got attached to this idea that sort of arose in the Fortran IBM world of having, not the only place it arose actually, but being able to represent character strings as things that computers could deal with, and that led to things like ASCII and well, earlier epsidic, this way of saying will represent an A by the number 65 or whatever else it is. So this mapping of character strings to numbers. Actually, I suppose there's probably a few trends here. I mean, one trend is sort of the naming of things, being able to refer to things by names that sort of relate to the kinds of things that we humans would talk about, as opposed to just saying it's the thing at number such and register number such and such. That's one thing. The other thing is taking more things in the world and sort of making them computational by saying, oh, we can take character strings and represent them in terms of bits. We can take logic represented in terms of bits. We can take numbers represented in terms of bits, and so on. There were other things, even with numbers. There were questions about how do you represent numbers, and the notion of floating point numbers, numbers where, so one thing you could do is just say, I've got this collection of bits, and the first few bits represent the ones column, the tens column, the hundreds column of the number, the 1/10ths column, the 100ths column, etc. That's a fixed point number. Then there's the notion of a floating point number, where you say these bits represent the mantissa of the number, and then it's times 10 to the power or times 2 to the power, such and such a thing. You can float the decimal points around wherever you want. And that was an idea. When did that come in? Probably the 50s was when that was introduced, but it then got kind of this IEEE floating point standard got introduced. I'm not a big fan of that. I think it's led to just all kinds of crazy problems because it doesn't tag the precision of a number. It just says, here's a number, it's got this number of bits, just deal with them how you will, without saying, oh, well, actually, most of these bits are nonsense. So in any case, in terms of the development of kind of ideas in kind of programs, there were some things that were actually very early ideas, but they didn't catch on. There were ideas that had come from combinators that came into Lisp, and that was defined, at least theoretically, in the late 1950s. Ideas about pure functions, anonymous functions, lambda functions, whatever you call them, functions where instead of saying we've got a function f of x, and that's equal to x squared or something like you would in sort of traditional math, you can have a lambda function where you say it's just this pure function. It's just the f. There's no f of x, it's just the f. And you can carry around that function on its own and apply it to things. That was an idea that actually arose in the 1920s with Schoenfinkel and combinators, but it was first made into something like a software thing by John McCarthy in the late 1950s in the specification of Lisp. It finally became something that was widely used. I mean, I started using it in SMP in 1979. It's been used in Wolfram language since the beginning in 1988. It has finally become fairly popular across lots of different languages and so on. This idea of you just pick up a function and think about it on its own, and you can operate with functions on their own. I would say that what were some other big ideas? Another big idea in the very early days, just as one had said that variables representing pieces of memory were named, so were functions, blobs of code that could execute. Another thing that got named, another thing that got specified were go-tos. You'd have a bunch of code, and there'd be this operation, this operation, this operation, this operation, and so on. And you would be able to say, okay, I'm running one instruction, then the next, then the next, then the next, and then it's go to some other place, and you could label the go-to. Turns out that was a very ugly way to program. Turns out it was very hard to tell what was going on. It turns out that wasn't a very modular approach to programming. The whole idea that you should be able to take programs apart and think about them in a modular way is an idea that I would say started to gain serious traction probably only in the 1980s, although it was certainly a known idea in the 1970s, but it wasn't an idea that people really focused on. Okay, so there are many kinds of steps in kind of other kinds of things that were sort of an early ideas in software were arrays. The idea that Instead of just having an individual number, you can have an array of numbers. You can have, for example, a one-dimensional array or a two-dimensional array, and that you can do operations perhaps on the whole array at a time. APL, for example, in its original specification at the beginning of the 60s, was a language very much oriented towards specifying just add 1 to the whole array. You don't have to specify separately, okay, make a loop, add a 1 to the first element, second element, and so on. That's obviously an idea that in Wolfram language we take seriously. It's an idea that is very natural for people. The only time it isn't natural is when they've been taught, oh, computers just do one thing at a time. You have to make a loop to do this, then this, then this. And there's a certain amount of unlearning that has to be done when people say, no, you don't have to do that. In Wolfram language, for example, you just add 1 to the list, and it'll add 1 to every element, and so on. But that was another idea, was the idea of arrays. Another idea, which was kind of a low-level idea, was the idea of pointers, which was sort of popularized by C, and that was the idea of so one of the issues had been when you have a subroutine, for example, and you are going to give data to the subroutine, how do you give it that data? Do you say, when you call the subroutine, are you taking the values of certain variables, X and Y and so on, and just feeding those values to the subroutine? Or are you instead taking the names X and Y and telling the subroutine, go look for the data in the place that corresponds to the name X, the name Y, and so on? In Fortran, there's this idea of call by name, which says you at least in early Fortrans, I don't actually know how it's evolved today, but you basically just say what you want subroutine is the thing that's called X. So you can go and find that, as opposed to giving it the value. That's part of the reason that recursion wasn't possible, is because the thing that was called X one time wouldn't be the thing that was called X the next time that same function was called. But so this idea of just call by value, that was an idea that was sort of became kind of the default in later programming languages. But then there's another thing, which is call by reference, where you're basically saying, instead of the X, I want to refer to X by the place in memory where X is stored. So that's the idea of getting the address of X. I should explain that sort of a big idea that had arisen in the late 1950s was the idea of compilers, where you would take a higher level language, a language that was more sort of human friendly, and make it and then automatically turn it into something which was operating at the machine code level. Originally, Fortran was the formula translation language, where the idea was to write something that kind of looked like math. It wasn't that much like math, but somewhat like math, and translate it into the machine code so that the machine could execute it. There have been other sort of ideas. I would say that an idea that was popular in the mid-1980s was the whole object-oriented idea. That was particularly relevant when you're building user interfaces, and when you want to say, I've got a window, and it has all these various different things that can be done to it. I've got another window, and it can have things done to it. And this idea of organizing programs so that you would organize it in terms of objects and methods and so on is an approach to organizing programs that particularly good if you're building things like user interfaces. It is not as general as you might think it would be, but it's useful for those purposes at least. And by the way, a big trend coming into the 1980s and so on was bigger programs. How do you deal with organizing bigger programs? What are some concepts in working on bigger programs? And in a sense, there was a merger there between the technical side of how do you organize programs and the management side of how do you organize teams working on programs. And then there were between and I think that was kind of a and that things like the object-oriented approach were sort of combination, in a sense, ways of thinking about management. People talked a lot about, in the 80s, talked a lot about software components and being able to plug one piece of software into another piece of software and so on. that kind of turned, I suppose, into the idea of libraries and things like that. I think there are a couple of big ideas which I've been much involved in, which are, so one is the idea of functional programming, the idea that you think of things in terms of functions, and everything that happens in a piece of code is just applying functions to things. That's an idea that I've made a lot of use of. It's certainly not my idea, so to speak. What's ended up happening is, I think it's a very useful organizing idea of just say, how do you make a function out of that? How do you make something where you can sort of describe what you feed into that piece of computation and what comes out of that piece of computation? How do you describe those things? And then you're sort of packaging that piece of computation in this thing that is a self-contained function. It doesn't have tentacles hanging out, going all up to sorts of other places. It's this self-contained thing. That's an important idea in sort of how you think about things computationally. But then there's the idea of sort of just working with the disembodied functions and building up kind of higher level functions, doing things like, in the simple case, mapping a function over a list. Or another thing would be, composing functions together, doing things where functions are operating on functions to create kind of higher level functionality. So that's another idea. Another idea I've been deeply involved in myself is the idea of symbolic programming. The idea that it's kind of the question of how do you represent things in the world for a computer? And sort of in the end, it's got to be represented in terms of bits. But that's far away from the way that humans should think about it. And, if you're representing a city, how do you do that for a computer? And if you're representing an image, how do you do that for a computer? And being able to kind of have this notion of things being represented symbolically, where they don't have to have sort of values where the computer can explicitly see, oh, I can turn that into a bunch of, where when you run the program, it's like turning it into something like numbers or strings or something where you can immediately imagine, I know how the computer's going to represent that. It's something where you can maintain the thing in a symbolic form that we can interpret in terms of the real world, but which we can't necessarily readily interpret in terms of the way it's represented in bits in the computer. And so sort of a version of that is you have an X. What does the X mean? Well, often you'd say, well, X has to be something. What does that mean, be something? It might mean it's got to be a number that you can represent in terms of a collection of bits. It's got to be a string. You know how to represent that in terms of a collection of bits. But in a symbolic language like Wolfram language, for example, X can just stand for itself. You can just manipulate X on its own just as X. And you might use it for algebra. You might use it to represent something. And once you have that idea of symbolic things, and once you have the idea of functional programming as well, you can represent things with symbolic heads for functions. So you just have an F of X, or it might be something that says, I don't know, city of whatever. And that head of this thing is symbolic. It's both handling things at a functional level and dealing with things symbolically. And the thing which has been sort of a surprise to me, I suppose, is this idea that you can think about programs and think about representing things computationally by just building up these symbolic expressions, just building up functions with symbolic heads applied to arguments that might be symbolic and have other functions with symbolic heads and so on, that you can use that to represent all kinds of things in the world. In fact, kind of everything in the world, it seems. You can use that to represent things you might deal with on a computer, like a user interface, like a collection of programs running, like all kinds of things, like a program itself. That has been a very powerful idea that certainly in my efforts over the last 40-something years, that's been sort of a guiding principle, is represent everything in terms of symbolic expressions. Important idea, not widely understood, even now, 40 years later. Another big idea in my life of dealing with these kinds of things is the idea of transformation rules on symbolic expressions. The idea that you can represent what computers, the part of what computers do that we humans find useful, in terms of saying you've got a symbolic expression and it's more or less like this, but there's some pieces we haven't yet specified. You're defining your function to be something that says, you're defining things to be saying, whenever you see a symbolic expression like this, it gets transformed into one that's like that. that idea, which is ultimately a very simple idea, turns out to be super powerful. And it's the idea that all of Wolfram language is based on. It's kind of the idea that I've been pursuing for the last 44 years now. And I think and by the way, ironically enough, a version of that idea is exactly the idea that is at the foundation of our physics project and our current understanding of fundamental physics. I did not see that coming at all. The fact that this transformation rules for symbolic expressions thing was something that I had built as a matter of technology for constructing computational languages was sort of a completely separate branch from my thinking about how should one think about sort of the computations that happen at the fundamental level in the universe. The fact that those end up being the same is one of those personal ironies, I suppose, that I certainly didn't see coming. Well, I'm sure I'm forgetting a lot of things about sort of the evolution of software. I mean, I suppose, okay, another thing I might say that sort of in my own area is sort of there's what do you take for granted when you walk up to a computer? You know, is it the raw hardware? The first computer I used, all you had on the computer was the raw hardware and a few initial instructions that were burnt into at location 8181 on the computer. You pressed a button to say jump to location 8181, and it had these initial instructions that were actually implemented with transistors and so on in the computer. And that was the only thing that was sort of intrinsic to the computer. Later on, there were operating systems that sort of came with computers or that you came to expect to use on a computer, then languages that you came to expect. Then later on, things like networking, user interfaces, those kinds of things. The thing that has been sort of my big push for the last, I don't know, 20-something years has been this idea of computational knowledge as a thing to take for granted when you kind of just walk up to a computer. That it is the case that you expect that your computer is just going to immediately know about things about the world in computational form, things about algorithms and so on, that you're going to be able to talk about cities or distances between them on the Earth, or things about algorithms and so on, and that your computer is just intrinsically going to have that stuff built into it. And that's what we've been trying to achieve over all these years with Wolfram language. I'll mention one other thing in the development of software. So I've talked about how one of the things that happened starting in the 80s, I suppose, was people started to think about how are we going to organize these big software systems in terms of the way that the code was organized, in terms of the way the code is managed, in terms of source code control, in terms of the way teams work on things, in terms of the way the things are specified and so on. And there are these, the waterfall approach, the agile approach, all these kinds of things are different management schemes for thinking about how do you develop a piece of code, because in a sense in the end what you need is something where you are saying this piece of code is going to do something that's useful to people. Well, what's the thing you want it to do? And then how do you build the code so that it is as maintainable as possible, has et cetera, et cetera, et cetera, as extensible as possible, and so on. I think the one discipline, so to speak, that people still have not understood is incredibly important is kind of the whole idea of language design, functional design of software. People, this thing that I've spent a huge amount of time on, and I live stream some of my efforts in this regularly. I just did a live stream just before this, actually, that this idea of how do you design the way that a software system should look at the level of functions, at the level of a language, and so on. And to me, this is the most concentrated form of kind of human understanding that I know of. It's something where you are trying to get ultimate sort of operational understanding of different areas. You're trying to make things, you're trying to boil things down to the point where there are you're getting the essential features, and you want to do that in a way that's very consistent and coherent, so that, and this is the sort of big thing of Wolfram language, so that all these different pieces, whether you're doing image processing or machine learning or audio processing, or whether you're doing all these different things, they all fit together. They all are consistent, and the things that apply to one of them apply to others, and so on. And that process of doing language design, which is really a process of going from the complicated requirements that people have down to the essence, the primitives, to see how things fit together, that to me is a very a very important and very high leverage intellectual activity, and very difficult one that, well, I mean, I enjoy doing it. I think it's a deeply, deeply underappreciated activity. I mean, eventually people will realize that that's kind of one of the sort of the pivotal intellectual activities that was the determining factor of whether people could actually think in a language, whether people could actually build a big tower of functionality and so on or not. And that's why I spend so much time on it, is because I think it is this sort of pivotal piece of kind of this pivotal, very essential core kind of intellectual activity. And we slowly diffused the knowledge of kind of how to do language design, but that's a thing that has happened extremely slowly, I would say. But it's something where that's something which I think will be seen eventually as one of the sort of pivotal realizations that was an important thing. Sort of and it's very much, it becomes very much more realistic when you have ideas like symbolic programming and transformations on symbolic expressions and so on. It's much more, you have much better sort of raw material to operate with in terms of language design when you have those kinds of ideas, because this kind of symbolic idea means that, for example, you can take programs apart into arbitrarily small pieces, because at every stage, the things the programming is operating on are just symbolic expressions. You can just pick one up, do something with it. It's not, oh, it's some data structure embedded inside the computer. We can't actually pick it up and do things. We have to write other code to be able to read in, write out that data structure. All right, very long answer to that. Let's see. Okay. Oh my gosh, lots of interesting questions here. All right, I'm going to take one from Baines here, saying, I watched recent NASA rocket launch and wonder what's new in the past 60 years in terms of launching rockets. It's surprising that, the principles are very much the same. Even the designs, I gather, are rather the same. I mean, I think when early, even SpaceX, for example, licensed, I think, early Russian designs that, I'm sure they've been developed since then. But, one question is, why is it hard to make a rocket? And, first point is you're pushing it from the back and it's got to go up straight. And so that was a thing people like Goddard in the 1920s, I guess, started figuring out, how do you make a control system where you can actually have the thing, have the rocket nozzle sort of be controlled so that when you push it from the bottom, it doesn't just fall over. That was the first step. That problem's been solved. It's why if you watch a launch from an Apollo launch, I don't know whether they do this still. It always used to be the case. When I was a kid, I watched the Apollo launches, and one of the notable features on the big Saturn V rocket, they would have these black stripes and white stripes painted on it. And I was like, why do they do that? And I figured out, oh, because if you're taking if you're looking at the video, if you're looking at this thing, you can tell if it's turning. You can tell if the thing is rotating around, if it's got big black and white stripes. Otherwise, it's just a big silver or white rocket or something, and you can't tell whether it's twisting. But in any case, I think, the big thing is that, rocketry is about burning stuff, and it's about keeping materials at the point where they are undergoing complicated phase transitions, and you end up with this amazingly complicated sort of set of pipes and tubes and valves and so on, and combustion chambers and all this, in order to deal with the sort of nasty detailed properties of materials right at the point where they're combusting. And I gather what usually limits rockets is the how much the turbo pump that's just pumping fuel and oxidant, if it has that, into the combustion chamber. You just got to do that faster, faster, faster. So I don't know what's. I mean, I would have thought that there were things that have been made possible by modern sensor technology that weren't there before. And I know certainly in terms of the sort of early warning of if something's going wrong, there is a bunch more that's been done there. But I don't think that the fundamental design how you make a combustion chamber and things like that. I don't think that's changed very much, and I don't think that I think sort of the flight controller that means that you push it from the bottom and it keeps on going up. I think those principles have certainly transitioned to being electronic rather than mechanical as they were originally, but I don't think that's changed that much either. I think, when you look at, it's a little bit shocking that the design of, that you see for the, the outer shape of some rocket is the same. Well, the reason it's the same is because it's a good shape for hypersonic flow, and that hasn't changed. Now, is there some design? Is there some super clever design which, like for airplanes? Airplanes had straight wings, and then it got figured out you put these winglets at the end that help with transonic flow, and then winglets became kind of a designer feature of airplanes, and everybody wanted winglets because they look cool. But there are details like that get figured out, and different wing shapes and so on. And I suspect some of those kinds of things have been done for rockets as well. And I would think also that materials, I mean, the world of, the tiles on the shuttle, that's been upgraded a lot, but you don't immediately get to see that. And also, I think in terms of the actual controls, I mean, inside the all of that stuff is dramatically different than it was before. But I think in terms of sort of the outer shell and the basic ideas, I think they're fairly similar. You might say the same thing about airplanes. I mean, what's changed, since there've been jet planes, what's quotes really changed? And the answer is a lot of things on the inside about carbon fiber and, and composites and things like this, different kinds of materials. And, if you look at the detailed patterns of a lot of studies from computational fluid dynamics and so on that have allowed optimization of the shapes of planes and things like this. But, the big picture, I guess, has not changed very much in that case either, even though in that case also tremendous changes in the avionics, the control systems, the computerization, the kind of sensors, all those kinds of things. Let's see. All right, let's see. Oh boy, Aaron is asking a question I don't know the answer to, but I'm wondering about, is why did American English develop common words for every third order of magnitude, like million, billion, trillion? Other languages seem to have different words, like lakh, for example, in Hindi. I thought lakh was 10,000. Is it 100,000? I'm not sure. But this question about the modifiers that exist in different languages to represent kind of different orders of magnitude. When I was a kid, billion in British English meant million, million, which is trillion in American English. Super confusing, because in the US, this idea of going up by threes was the thing that came in. I don't know. I mean, I don't know the history of the kind of the terms billion and trillion and quadrillion and so on. I think I mean, I kind of wonder what was the first domain in which, well, millions were, no doubt, people had millions of dollars. They didn't have billions of dollars. That didn't become a thing until much more recent times. So, I don't actually know where those words first came into use. I'm kind of thinking that, the things that were referred to were million, million, and then somebody said, no, let's just call that a billion. And that was, the British English version of million, million. And then that evolved into, and evolved differently, and I don't know exactly when in the US. So I'm afraid I don't know the answer to that. Let's see. Des is commenting here. Remember a comment from an old programmer saying the first time they saw a screen used with a computer was in the movie 2001. It's certainly true for me. I mean, I saw that movie came out in 1968 when I was 8 years old. was the first movie I ever saw in a movie theater. There's a piece of personal trivia. And in fact, I wrote about this actually in 2018, when the 50th anniversary of 2001. It was it's a movie that had yes, it had screens. It had which were of course made in a purely movie kind of way. It wasn't, but computers back in those days, I mean, I first saw a computer a little bit after that time actually, and it was a mainframe computer, so you couldn't actually get to the computer. It was behind, you know, sort of armored, kind of a very sequestered, very high priest type setup. With, I don't remember whether people actually had white coats, but they might have done around the computer. And you know, the only thing you got from the computer was a printout put in a wooden pigeonhole, and you would feed in a card deck that you had made separately. So that was the first level of interaction. The original thing, at least in British English, I'm not completely sure about American English. Gosh, this is a sign of me having moved from one country to another at a certain time. The early name for a display for a computer, at least in British English, was a VDU, Visual Display Unit. And I first, oh gosh, when did I first see one of those? Probably 1973, 1974. And those first were used in various kinds of transaction processing systems, I think. I mean, I think like people doing airline reservations were starting to use those and so on. As a thing that was, by 1976, 1975, 1976, they were everywhere. But those were displays that were character at a time displays. And so they would have, you know, a typical technology was they would have a CRT, a cathode ray tube, they'd have an electron beam, and there would be an actual piece of metal that would have characters carved out of it. And the electron beam would be sent through the A-shaped hole in the piece of metal and then to the screen, and then it would produce an A. And as the thing scanned across, it would be, with an electric field, it would be moving the electron beam to go through the, you know, the C place in that piece of metal and then to the right place on the screen. And that was kind of the technology. You know, early computer terminals, that was the technology they used. It was purely worked that way. There was a different technology which came from oscilloscopes. And oscilloscopes, you know, you just put a voltage on and you can make that spot go anywhere you want. And so there was a technology of storage scopes, oscilloscopes, where I think, first of all, the actual phosphor was something that would continue to glow when the dots had moved on, so to speak. And so Tektronix was a company famous for making these storage scopes where you would make graphics by just having that dot. You would control where that dot went in sort of the XY plane, and you would sort of paint on there, and the phosphor would kind of maintain where that dot had gone. And so that way you could build up graphics, and then you could print from that. And it was typically some kind of thermal printing process where you could get sort of the output that way. And that was sort of the early way to do graphics, along with pen plotters, where you were doing the same kind of thing as specifying the dot with XY. You were specifying the position of the pen, where it would just have these two sort of, you know, things with two runners with belts and so on, where you're moving the pen in the X direction, the Y direction to draw your picture or whatever. And that was kind of that early technology. The first place where the big innovation came in the beginning of the 80s was bitmap displays. That was, I probably first saw a bitmap display when I visited Xerox PARC in probably 1979, maybe. I think I also saw those at, visited IBM Research maybe a year or two later. But that was a place where you would have, the idea was you have this display that's made of lots of pixels, 1 million pixels or whatever, and you would have a place in the memory of the computer where you would assemble a pattern of bits that were corresponding to what you wanted the pixels on the display to look like. And, in the early Xerox Altos, it was very much, Xerox was a company that was involved with dealing with photocopying onto paper and sort of the 8.5 by 11 sheet of paper type metaphor. And the Alto had the screen that was, most screens had been, as they are today, were kind of wider than they are tall. The Alto was taller than it was wide, like a piece of paper, and also had the innovation that it had black print on a white background, whereas all of the CRT type things, the screen was basically black, except where the electron beam had painted on the phosphors, and then it was green or whatever. And I find it very ironic that for me, the black on white was kind of the great innovation of the early 80s, of when computers became more kind of familiar and more kind of like printing on paper. And the idea of, the green on black was like the ancient stuff that, was all determined by the physics of cathode ray tubes and things like this. And I find it ironic that today, with kind of dark mode and so on, people are like, wow, we can have, light type on a black background. And I'm like, that was how it used to be in the ancient world, when that was what was constrained by the physics and electrical engineering, what was going on. Now we can do other kinds of things. But I just find it ironic that that's the way that developed. But yeah, I think the way that sort of the bitmap display was really, well, the Xerox kind of Office of the Future type thing didn't really as such catch on, but those ideas got transported to the Mac, and got transported to things like the Sun workstation and so on, and gave us kind of computers as they are today. Let's see. William is asking, why is ChatGPT blowing up now when GPT-3 was known in 2020 and GPT-2 in 2019? Because it's much better. If you try and do, what ChatGPT is fundamentally doing is going from a textual prompt, and it's saying, how would that continue? What's the sort of average way that would continue based on everything you've seen by crawling the web and so on? And if you try those things in GPT-2, GPT-3, they don't work that well. It doesn't make the interesting story. It doesn't make the thing that really is going to make you say, wow. I don't know exactly what it is, and I'm not sure anybody really completely knows exactly what it is that's made that jump happen. I think it's partly the reinforcement learning training, where one's taken actual humans and said, okay, generate a bunch of essays. Now say which ones look really like essays and which ones look kind of cruddy and miss the point. And one's kind of given that feedback. I think it's also a certain amount of tuning of how much randomness is there in the way those continuations work. It's also additional training material, that it makes a difference that you've trained it on, however many billions of pages as opposed to only hundreds of millions of pages. Those things make a difference, but I don't think we know why that transition. Well, as an operational matter, it's partly the reinforcement training that's definitely had an effect. It's also just good engineering done by the folks at OpenAI to provide something that has a form factor that that just has been structured so that it can produce essays, poems, whatever else, which I think more a piece of engineering than it is the raw language model of the neural net and so on. But yes, it's a, I mean, the reason it's blowing up is because it's well engineered, well presented, and it actually works. And and these previous things were just not that interesting. I mean, I tried them, and it's like, yeah, this is cool. And I mean, we've had in Wolfram language, we've had a sequence predict function which uses sort of the progressively better technology for like predicting textual sequences in English, and it's not particularly useful. Now it has become so. I mean, there were always little precursors of this in some of the systems that we used for grammar checking, things like this. But this is a real leap, and I think it's telling us something about sort of how brains work and what level of sophistication we should expect in the language production in brains. I'll have more to say about that sometime soon. Okay, there's a question here about how much do I think from spare parts, how much do you think real science and technology is shaped by ideas from science fiction? You know, more than rather a lot, I think, surprisingly much. Maybe only by science fiction that becomes popular, maybe more by movies than by written science fiction. I think that sort of movies tend to provide a useful kind of cultural sort of reference point for kind of what are we trying to build? Oh, we're trying to build the Star Trek computer. What are we trying to build? We're trying to build a flip phone that's like the Star Trek communicator. You know, these are kind of reference points. And sometimes, I mean, it is interesting the extent to which one can imagine what will be possible, and then you know, eventually the technology gets to the point where one could do it. Now, you know, is that going to be possible for everything? Is it going to be possible for, let's say, cryonics and human hibernation? Is it going to be possible for faster than light travel? Is it going to be possible for I don't know what various kinds of, well, it depends what pick your movie, so to speak, what the different technologies are. I think some of them will probably run into kind of, well, it won't be done that way. That's a kind of physical constraint. But, you know, you see these things where you can imagine it. I mean, the idea of a sort of a book-like object that was electronic, that's an easy idea. I'll give you an example of how this plays out. You know, back in 1987, I was playing professor at University of Illinois then, and I just started this research center. I'd gone there to start this research center about complexity and such like. But anyway, there was a Apple computer, as it was called then, had this competition for students to design a personal computer of the year 2000. And so it was a rather nice enterprising group of students at University of Illinois who came to me and said, will you be, they needed a faculty advisor with this project. So I said, sure, sounds interesting. And so, you know, we came up with what the personal computer of the year 2000 would be like. And I have to say, I kind of avoided talking too much about software because I was actually working on software and I didn't want some complicated entanglement about that, but we mostly concentrated on hardware. And as many people pointed out, the thing that we predicted back in 1987 was extremely close to an iPad. And although the iPad didn't come out for another, you know, decade after that, you know, it was like, it's a small thing with a certain form factor, has a screen, it's a touch screen, it has this networking, it has various attributes about how that works, et cetera, et cetera, et cetera. In a sense, those were inexorable predictions. I wasn't very impressed with myself, so to speak, that we could come up with those predictions. That they were kind of like, well, you see which way things are going, that's going to happen. As I've said many times, one of the things that at least I find much more difficult, I think other people too, is you make a prediction about what will be possible, and you're right about what's possible. You can't easily predict the time frame over which it happens. And sometimes things happen, like, you know, take ChatGPT, for example. I must say, I'm surprised at how comparatively easily we've gotten over this threshold, and we've got to the point we've got to now. But that something like this would eventually happen, yeah, you know, that's unquestionably the case. That it would happen suddenly is interesting, and that it would happen in 2023, you know, 2022, 2023 was not something I could have readily predicted. Even seeing, you know, even given that I've been following, you know, GPT-2, GPT-3, I couldn't have told you. And then in another year, boom, we're going to get to the point where this is really interesting. I couldn't have said that. I'm not sure anybody else could, including the people working on these projects. I think nobody knew. I think it's telling us something scientifically important, but I think it's a surprise. And I think, yeah, anyway, so I mean, I think in terms of it's interesting to see what in science fiction hasn't come to reality. I mean, people always talk about, when people talk about gestural interfaces, you know, being able to move your hands around to make things happen, they always mention Minority Report, which had a nice rendition of kind of gesture-based, you know, interfaces. Now, of course, there is some gesture-based interfacing in VR. I don't know how popular it's become. I must say, when I've used it, it's been kind of not that exciting. You know, I kind of feel like there are places where gesture-based interfaces should be important, like shaping things in 3D and so on, but I don't think it's quite happened yet. But probably it will, and that's something where everybody's going to refer back to Minority Report, because that's the place where people really saw, these kind of gesture-based interfaces being sort of put into practice. I think, voice-controlled computers, well, that was in Star Trek, that was in other things. There was, it was obviously in 2001. Yeah, it's an interesting question. What things there have been in, I don't know, I'm going to show my knowledge or lack thereof of popular culture, but the kind of bionic man type thing I suspect many of those kinds of sort of technology, implanted technology type innovations, those are either here now or are coming. That's another kind of direction. Although the kind of, as I recall, that character had the kind of the just think about focusing the built-in eye. We're not quite there yet with artificial retinas and things, but probably will be. I think there are, oh gosh, what other things are there? Maybe somebody can suggest some, but sort of things from science fiction. I mean, there's plenty of things about the sort of social order from science fiction, which for better or worse, some of those have come to pass. There's plenty of terrible dystopian expectations from science fiction, which some of which are strangely and disappointingly coming to pass. But in terms of technology, I'm not sure. William is commenting, the thing about ChatGPT is it uses the same architecture as GPT-3, same number of parameters. The fact that fine-tuning can create such a leaping capability suggests we are in a hardware overhang. I'm not quite sure what that means. It's I don't quite know what that means. I'd like to know what that means, actually. Let's see. Kat is asking, has there been any technology in history that's been perfected, like the wheel, where or is there always room for improvement? What tends to happen in technologies is they get to some point and then they kind of stabilize for often a long time until some very different thing comes along. I mean, I'm always struck by printer technology, for example. There was a time when you were getting new printers every 6 months because there were new things and so on. And then the printer that's sitting under my desk, I don't know how long it's been there, but probably 10 years now. And it's a thing where it got to a certain level of capability, and it got good enough that that's what you can get. There wasn't a lot of ability to sort of engineer further. We see the same thing. I don't know, take CPU chips. There's been sort of progressive. There was a kind of Moore's law kind of growth of speed of computer CPU chips for a long time. Then some things kind of leveled off, and one had to have innovations in other places like multi-threading and GPUs and things like this. I mean, I kind of tend to think that there's usually, given a sort of a big idea of some piece of technology, there's a point where it gets to be sort of fairly stable, and then get sort of incremental improvement for a long time. You talk about wheels. I don't think it's true that there's no innovation in wheels. I mean, I've seen, gosh, probably even in the last year, I've seen innovative wheels where they have different ways to have different kinds of sort of suspension mechanisms instead of having tires and things, different kinds of axles, different mechanisms for being a wheel that can go over complicated terrain. There are wheels that I think I've seen them for rovers, for planetary rovers and things, different kinds of wheels. So I think even the wheel, has definitely not gotten to the point where it's stabilized. Now, I don't know, the paperclip or something, that's probably been the same for 100 and something years. But, of course, there are different kinds of paperclips, and maybe there comes a time when there's a very different thing you need from your paperclip. And so then there's sort of a disruption in that area. I mean, I think I think the pattern, and then there are domains in which it's almost a fashion statement that causes there to be sort of continued innovation. It's almost, independent of the raw capability of the system. It's like it's differently dressed every year. And, there are many industries like clothing, for example, where there is a sort of driver of change that has nothing to do with technology innovation. It's not, there have been new materials and so on and new ways of manufacturing clothes, but hasn't changed that much. What changes is, well, one day there's a fashion for, this kind of, hoodie or whatever. Another time there's a fashion for this kind of thing. Waistcoats maybe will come back in. I don't know, maybe they have, and I haven't paid attention, but that there'll be these drivers that are more a matter of the kind of the herd of us humans saying, whoa, that was a really cool thing, and I'm going to follow that too, than it is a matter of sort of the driver of innovation in the actual core technology of what's going on, or even the supply chain of what's going on. So I think that's yeah, a few comments on that. Memes is commenting about printers, that papers jammed 30 years ago, paper jams today. Yeah, I think paper jams got a bit better, but I don't know why I don't know. I'm surprised that there aren't ways of using modern sensor technology and so on, and modern control systems and MEMS and all this kind of thing to just, banish paper jams forever. I mean, it reminds me, I was at the Consumer Electronics Show a few years ago, and one of the tremendous attractions, giant line of people wanting to see it, was, I think it was called the Laundroid. It was a laundry folding robot. And it's something where that problem is pretty hard of sort of the, the folding a thing with robotic hands or whatever. It turns out to be pretty hard, and probably eventually it will get solved, but it's maybe the paper transport problem is similarly hard. Spare Parts is commenting about the paperclip. Let's not ask the AI to design a new type of paperclip. Yeah, there's a famous kind of story of the alignment of kind of AI interests with human interests, which is you tell the AI its goal is make as many paperclips as possible. And then, of course, what it does eventually is to turn all humans in the world into paperclip material, which is presumably a bad ending for us humans. And if there's a civilization of the paperclips, well, that's a different story. All right, let's see. Yeah, William is commenting, paper jams happen today, but paper has become irrelevant. Yeah, I mean, it is true that a single ream of paper that I put in my printer seems to last me several years now. I really don't print very much. I've noticed also another example of that is, back in the day, people were like when you traveled from place to place, it's like, oh my gosh, it's going to take me this amount of time to drive from here to there. That's terrible. I can't, how am I going to, I'm wasting an hour. It's terrible, et cetera, et cetera, et cetera. And then there were cell phones. And ever since there've been cell phones, it's like, well, I've got calls I wanted to do, and, I set them up for when I'm driving from here to there. And I'm like, great, this is all efficient. And, it's same with other kinds of, there are laptops. I remember when I first had a portable computer in 1981, maybe. I had an Osborne 1 sort of suitcase-sized computer that I think I may have been one of the first people to take a computer through airport security at Los Angeles at LAX airport. It was kind of an interesting thing. But it was a computer that was not very portable. I remember the first actual battery-operated computer that I had was a thing called the DG1, Data General 1 computer. It must have been in 1985, perhaps. That I sort of proudly took on a plane and was able to actually do things, truly on the go, so to speak. But these things, yes, these things affect sort of the importance of having the supersonic plane and so on. Starts to seem a little bit less when you realize, oh, I just get on a plane and I'm there's some cases where it might be useful to get there quicker, but it's kind of like I'm gonna just open up my computer, I'm gonna start working. I have a different view than the one I normally have, but it's pretty much the same kind of story. Yes, I think that's a it's often the way. But I mean, there's plenty of technology that we still have that is very old, and we still have roads. We still have maybe one day roads will become irrelevant because flying, you'll always fly from here to there, and nobody will care about the roads. So yes, that could happen, but we're still at we're at a few thousand years and counting on that particular technology. And then there are technologies that that we sort of are close to us humans and we're used to, and so on, that I kind of think will be around for a while until we have significant changes in kind of the character of humans and so on. All right, I think I should probably wrap up well in a moment here. Let me see, maybe one more question that might be okay. There's a question here about physics from Zayden about when and why was dark energy hypothesized? Oh, dark energy. Okay, I thought I was reading that as dark matter, because the answer for dark matter is it's 100 years. It's people looking at the rotation curves of galaxies. Dark energy is much more recent and has to do with people's estimate of the expansion rate of the universe. I kind of think that both dark matter and dark energy are probably not, they're kind of mis-theories, so to speak, in the sense that they are an attempt to fit into current paradigms for talking about things that really should be thought about in terms of different paradigms. It kind of reminds me greatly of something I've been studying a bunch recently, which is the history of the theory of heat, and where people believed, well, heat is a fluid because fluids, we understand what fluids are. They flow from here to there. Heat can flow from here to there, etc. Turns out heat isn't that. Heat is, in a material, for example, is the motion of molecules, but that was just a different, paradigmatically different kind of interpretation of what something was than had existed. And that's kind of what I think is going to happen with dark matter and dark energy, but we shall see. William is commenting, once we get 3D nano-replicators, we won't need roads. We'll just teleport from place to place. Yeah, I think that's a very interesting thing of people talking about, how fast can we get from here to there? It's like, well, at what point, if the future of humanity is a bunch of, disembodied souls uploaded into some digital system, then the whole question of transportation becomes pretty moot. It's like, well, you're kind of, you're accessing a different part of memory. Your electrons are going from here to there, maybe, or you're just, it's no longer the physical transport of materials. And yes, I think that's, there are many purposes for which we could say right now, to somebody from the past, if we look at your average, video Zoom call or something, it's pretty much, it's something very close to some kind of teleportation in effect. By the way, that's a good example of this sort of future prediction thing. In the 2001 movie, there were video phones, and the idea of a picture phone had existed from the 1950s. And I remember I first used a video phone in what must it have been? It must have been around 1992. And the way it worked was you rented it from the phone company, and you rented two of them, and it, over a phone line, it sent data, and you got, it was kind of slow, but it worked. And it is remarkable that everybody knew video phones were coming. Everybody knew that was going to happen, but the timescale and the manner in which it arose was really not quite. I used to have the capability to do video calls on computers starting mid-1990s. I didn't do it very much. I did it very little because I didn't find it very useful, and because it had enough kind of detailed form factor issues that it wasn't attractive. Then by the, when was it? It must have been by, yeah, I first did a video talk at a conference in, I can work this out because it was right when one of my children was born, so 20, a bit more than 25 years ago. So which is what 1997-ish timeframe. That was when it first became sort of feasible to do a kind of a video conference talk, and without having very special equipment at well, it was still special equipment at that time. I then briefly tried sending a telepresence robot around as my proxy to various kinds of events. That was amusing while it lasted. It wasn't very practical. It's kind of been that's a technology where I kind of feel like one day maybe that will be a technology that will kind of come in, and one will be that will be a routine thing to do, but it hasn't happened yet. I mean, I kind of thought, for a while that the kind of the virtual, oh, I really want to go, see Machu Picchu, for example, but I don't want to go and, go to all the way to Peru and high altitude and all this kind of thing. I'm just going to send my drone there, and I'm going to do a kind of personalized tour where I can just be droning around or roboting around. It seemed like that was going to come in, but it didn't actually happen. Maybe it will in the future. I think maybe that will come in. Maybe that's what's going to come in. Maybe that's one of the use cases for moon exploration. Maybe the very few of us in the foreseeable future will end up going to the moon, just as very few of us go to Antarctica. Probably even less. I don't know, less to the moon or not. It seems maybe it's cooler in some sense to go to the moon than to go to Antarctica, so more people will do it. But maybe the thing that will happen is that there'll be a big, well, you don't get to go yourself, but you can be you can control this rover or this drone. That's how would a drone work on the moon? Good question. With the Mars helicopter, we know that it's possible to have drone-like flight on Mars, even though it has a thin atmosphere, and the helicopter blades go at the speed of sound and all that kind of cool stuff. On the moon, I think it's kind of like, well, actually 2001 had a moon bus, so which presumably worked with rockets, but yeah, that's a bit of a different technology than probably takes more energy, but I don't know how I don't know quite how that would work, but at least a robot wandering around on the moon, that might be the moon tourism. That might be the ticket for moon tourism, so to speak. That you pretty soon you find the moon is covered with random robot tourists, so to speak. I don't know quite what the speed of light delay associated with the 1 second speed of light delay associated with getting signal to the moon. I'm not sure quite how that would affect lunar virtual tourism, but oh yes, somebody's commenting here about the communication latency to the moon, right? Well, it's much worse for Mars. Doing that with a 20-minute latency, that's a funky thing. You'd have to have I don't really think that's going to work to Mars to do Martian tourism, but I mean it's just one of those things which maybe one day it'll be all the rage, but it hasn't happened yet. And that might be a feature of technology. It might just be a feature of human fashions and so on. I suppose it's it seems like, well, yeah. All right. Well, let's see. We should probably wrap up here, and I think lots of interesting questions. I thank you for that, and I think there were a few at the beginning that I absolutely didn't get to, so apologies about that. And maybe next time. Well, thanks for joining me, and see you another time. Bye for now.